Chapter 1 Overview. Have you ever thought to install several hosts into virtual machines by giving them different privileges of network access? For example, install 2 hosts into virtual machines. One host is used to access internet only and forbidden to access internal network, the other is used to access internal network only without the access of internet. There are many ways to achieve this goal via setting up the associated rules in external firewall or router. Our solution to this is to provide virtual machines in a controlled network environment without too much relying on extra network equipments. The Azblink Network Functions Virtualization Platform is a platform to create virtual hosts in a predefined network environment. The network zones are governed by the rules that can be added or deleted via web interface. The platform by itself is a firewall and router so that virtual hosts can be created in a well-planned environment from the very beginning. VPN is also provided by the platform for managing each virtual host from its console remotely. In the following sections, we will have the terminology used in this document defined and explain how those network operations work. Bridging and routing. We start with the introduction on bridging and routing. In terms of OSI, Open System Interconnection, model, if the data exchange is performed at data link layer, it is called bridging. If it is performed at network layer, it is called routing. In terms of TCP/IP/Ethernet, if where the data should go is UDGed by MAC addresses of the Ethernet frames, it is called bridging. If it is UDGed by the IP header of IP packets, it is called routing. While discussing data transmitted and received in data link layer, people usually use the term frame whereas they use the term packet in network layer. However, we are not following that convention so strictly in this document. We just refer them as network traffic either in data link layer or network layer. Illustration 1, Bridging Operation. Illustration 2, Routing Operation. The Ethernet we are referring to is consisted of physical layer and data link layer, usually known as PHY and MAC. An IP, Internet Protocol, belongs to network layer. Thus, if only Ethernet MAC address is examined and determined where to go, we say that it is bridging. Similarly, if IP address is examined, it belongs to the category of routing. For a network application to send out traffic to the other end, it is a complicated process with many details. When a host A is sending IP packets to another host B with known IP address, it still has to find out the MAC address of the host B. ARP, Address Resolution Protocol, will be used to find out the MAC address corresponding to that IP address of host B. The host A will first find out if the MAC address with respect to that IP address in the lookup table. If there exists MAC address matched, that MAC address is used. Otherwise, ARP query is broadcast over the network. The host B, or the gateway to the host B if it is in different subnet, will respond its MAC address if the request is matched with its own IP address. This document will not spell out those details, we will just outline some principles for the ease of planning and deployment. In general, if VLAN is not used, you can think that network equipments connecting to a bridge, Ethernet switch, should belong to the same IP subnet. For network traffic going across different subnets, there shall be a router sitting in between. In other words, router is with one leg siding in one subnet and other egg sitting in different subnets. Virtual bridge and virtual host. The Azblink NFV platform provides virtual bridges and virtual hosts so that the other operation systems, like Windows or Ubuntu, can be installed into virtual hosts. In the following sections, we will refer Azblink NFV platform or the system able to create virtual host as base platform, base OS or host OS, and the operation system in the virtual host as guest OS. On base platform, the network operation policies will be using virtual bridges as a unit for network operation. Once a virtual host is created, the associated virtual network interface, S, should be created along with the virtual host too. We will force you to choose the virtual bridge that each of the virtual network interface of the virtual host should connect to. Illustration 3, Traffic inside the bridge. Each of the virtual network interfaces of virtual hosts will be placed into a virtual bridge. If a physical Ethernet interface is also added into the bridge, a virtual host can access the network outside the base platform via that interface by bridging process. The virtual bridge also acts as a super Ethernet interface in the base platform so that it can have its own IP address with proper netmask to indicate the IP subnet it belongs to. You might view that the IP address of the bridge is the interface to reach the local network processes on the base platform. From the side of base platform, the network interfaces inside the bridge, no matter it is physical interface or virtual interface, do not have IP address set on those network interfaces on the base platform. On the other side viewed from the virtual hosts, the guest OS, S, can set their own IP addresses with virtual hosts. To be specific, assume the virtual bridge is named BR0 and it has IP address set on it. Inside the virtual bridge BR0, you might find Eth0 and other virtual Ethernet interfaces. From the side of base platform, those Ethernet interfaces within bridge do not have IP addresses set on them. In practice, this virtual bridge can be viewed as an Ethernet switch. The hosts connected via the same switch should belong to the same IP subnet unless VLAN is used. The reason to partition IP network into subnets is to isolate network traffic in a relatively local environment without global impact. For example, if an ARP request is sent, every host receiving the request should check if its own IP address is matched with the one in the request. If such requests happen quite often, the resource spent on this kind of activities might not be efficient given the fact that only one host is the real target of each ARP request. Therefore, network broadcast in IP network is only restricted in the same subnet, it will not cross to another subnet. ARP request is done via IP network broadcast, and there exist other IP-based protocols also dependent on broadcast. For those hosts relying on those network protocols to communicate with each other, they should be placed into the same IP subnet. There are chances that the network packets of the virtual hosts will go across the subnet. In the following diagram, if the gateway to the subnet of the target host can be reached via that physical Ethernet interface in the virtual bridge, the packets will go to that gateway via that physical Ethernet interface. However, the base platform is also with IP addresses on the bridges. If the base platform is with a network interface attached to the subnet that the network packets from virtual host are destined for, they could go via base platform through routing process to that subnet. Illustration 4, traffic going across the bridge to another subnet. To sum up, although the virtual bridges and virtual hosts are created by the base platform inside it, the base platform can be treated as a host that is parallel to the virtual hosts at the level of IP network. Whenever a network application in a virtual host wants to contact the base platform, it just sends network requests by using the IP address, ES, of the base platform. Other possible network operations, but we do not provide, in theory, there exist other operations between a virtual host and the physical Ethernet interface it is attached to on the base platform. We list some of the network operations that they are not provided on the product. The reason why they are not provided is that Azblink NFV platform is for server-type applications. The operation schemes indicated below might not be appropriate for server-type applications. For the sake of the completeness, we still discuss them here. In the next section, we will illustrate what Azblink NFV platform provides. Illustration 5, NAT on per physical port basis. The diagram above indicates that a virtual host is hidden after NAT, network address translation. The scenario usually happens when a virtual host is created on a base OS with IP address specified on the physical Ethernet interface. Once the virtual host is created, a corresponding bridge is also created by nullifying the IP address previously set on that physical Ethernet interface, and then, use that IP address on the bridge device, put that Ethernet device into the bridge, and give a private IP address to that virtual host. If the network packets from the virtual host wants to access to the hosts outside the base OS, the packets will be replaced with the IP address of the bridge device, the original IP address on the physical Ethernet interface. To access that host from the world outside the base OS, port forwarding is needed. The following diagram is a scenario that virtual hosts that are behind the same IP address under NAT, but they can communicate with each other with their own private IP addresses without going through NAT. This is implemented by connecting them on the same bridge. Illustration 6, allowing sending traffic between virtual hosts on the same bridge. There exists other scenario that the virtual hosts cannot communicate to each other although they are under the same IP address of NAT. They are only allowed to access the outside world via NAT, but they are not allowed to reach each other by using their own private IP addresses. This scenario sounds strange, but it might have the reason to do so when the two virtual hosts are owned by different companies in a cloud-based environment. Illustration 7, traffic not allowed between virtual hosts on the same bridge. The following diagram is to indicate that NAT function is removed so that the virtual hosts cannot access outside world, they only can communicate to each other with their local private IP addresses via the same bridge. Illustration 8, traffic locked inside a bridge. The operations mentioned above are not provided on our base platform. We only ask you to decide the virtual bridge that your virtual network interface should connect to. What if some of the functionalities, e.g. NAT, are needed during system deployment? We manage the system with firewall operations on the global arrangement of virtual bridges, each bridge is with its own functions defined in advance. For example, network packets from one subnet A, connecting via a bridge, to another subnet B, connecting via another bridge, might have NAT, network address translation, operation if it is defined in base OS. If it is defined, the source IP address will be replaced by the IP address of the bridge connecting to the destined network. Those will be introduced in the following section.